Greetings all. This is the Pencrest High School AP Physics 1 video series. This is video 6E, two-dimensional impulse and momentum. So we know at this point that both momentum and impulse are vector quantities. In one dimension, the direction is determined by the sign, according to our standard sign conventions. Right is positive, left is negative. We also know that when we expand into two-dimensional space, we have a lot more options for the direction. Most commonly, we're going to refer to mathematical directions using our standard mathematical axes. So recall that the mathematical axes measure angles counterclockwise from the positive x-axis. If the mathematical angle is between 0 and 90, the vector is in quadrant 1. Both components are positive. If it's between 90 and 180, it's in quadrant 2. X is negative, y is positive, and so on. I don't think it would take much for you to recall the status of each of the components. Two-dimensional momentum, because momentum is an instantaneous quantity, not a real big deal. We just have to express it in standard vector notation. We know that the magnitude is mass times velocity. It's measured in kilogram meters per second. The direction is indicated with a mathematical angle, and this would apply to both initial and final momentum. So again, P equals mv. We're familiar with that already. P prime equals mv prime. That would be our final value. The difficulty with two-dimensional analysis arises when we need to solve for the impulse. We know that the impulse is the change in momentum. That is delta P equals P prime minus P. Now, I've been very careful in showing this formula in that it always has vector symbols over each of the quantities there. This is the critical issue here. You may not, as we did in one dimension, just subtract the momentum magnitudes. Two-dimensional impulse requires all of the steps that go with vector addition. We're subtracting vectors here, but we know how to subtract vectors also. This means we need to find the components of the initial momentum, the components of the final momentum, subtract them, and then use the Pythagorean theorem and the inverse tangent formula on the resulting components. Report our answer in standard vector notation. If you need to refresh yourself on vector addition, you know where to look. You can look back at the old notes and the old videos if you need to. So here's an example of what a two-dimensional impulse problem looks like. The ultimate goal here is to determine the impulse on the object in standard vector notation. We have the object's mass here. We have its initial velocity in standard vector format. We're given a time interval, and then we're told that it's moving with a v prime or a final velocity sometime later. So what we're going to do, set up a table not unlike our component table for when we added vectors early on. I want you to take a look at the individual components that are listed symbolically in this table. The first row indicates the final momentum. We've got the x component here's the final momentum mv. That's the vector's magnitude. And then cosine beta prime will indicate the x component. Beta prime is the mathematical direction of the final momentum. Of course, the y direction, same vector mv prime times the sine of beta prime. These are the x and y components of p prime. When we look at the initial momentum, here's my initial momentum vector mv. Notice that there's an additional negative sign here. That's just to indicate that we're subtracting p from p prime to get the x and y components of the impulse. So we have delta px and delta py. Once we put the components in here and here, subtract them, we get the x and y components of delta p. Okay, it's also worth noting when we look at this image, the location of the object does not have any impact on the signs of the components of the initial and final momentum. In other words, it's what it's doing and not where it is. The initial velocity points to the right and down, so it's in quadrant 4, even though the object may be located in quadrant 3 according to where the axes are set up. The final velocity points to the right and up, which means v prime and therefore p prime would be in quadrant 1. So now, before we make any calculations with the data, can you make a prediction regarding the direction of the impulse? Okay, the initial velocity points to the right and down. The final velocity points to the right and up. Without any calculation, we can't tell about the x direction of the impulse because we don't know which x component is larger. We can tell, however, that the y component of the impulse is positive because the y component of the momentum goes from negative to positive. So I want you to think about that. Initially, the object is moving down in the y direction, and then finally the object is moving up in the y direction. Therefore, the impulse must be up. Okay, we could restrict the impulse to quadrants 1 or 2 because we know it's got to be in the positive y direction. Now, in terms of making calculations, you can verify these on your calculator. Make sure you're in degrees mode. When we get to the x and y components of the impulse, notice that they're both positive. Pythagorean theorem yields 123 Newton seconds for the impulse, and inverse tangent will yield 74.4 degrees for the mathematical direction. So again, when you look at the values that are in the table, notice the signs on the components in this this row for P, for the initial momentum. The initial momentum points to the right and down, but we are subtracting it. So we're subtracting a positive x component, and we're subtracting a negative y component. The negatives in the y component cancel, and we get a positive. So obviously, just as with one-dimensional impulse and momentum, we do have to be very careful about keeping track of negative signs. We can see once again the impulse has positive x and y components, indicating that it's in the first quadrant. Now you can imagine any number of combinations in terms of which way the object is going initially and which way it's going finally. In each of these cases, the mathematical analysis is the same. You can also expect that I'll ask you qualitatively about which way the impulse must point in terms of options. This one, for example, the object is moving to the right and down initially, and then it's moving to the left and down. We know that the x component of the impulse therefore must be to the left. The y component, we don't know. If we know it's to the left, it's got to be in quadrants 2 or 3, based on the fact that the x direction of the impulse has to be negative. Think about the other two, and think about any other possible combinations that you could run across. Okay, so that's it for 2D impulse and momentum. Next up, two-dimensional collisions. Until then, enjoy. See you again next time.